All right, here we go. Stats 5.4, central limit theorem. So we're gonna do a couple things. Today we're gonna learn about the central limit theorem. It's also known as the fundamental theorem of statistics, so it's kind of important. We're gonna review invert norm and normal CDF, and then we'll do a couple examples for you real quick. I think we have just a couple of examples on the back here. So review invert norm and normal CDF. So remember, invert norm is when we have a percentage and we want to work backwards to a z-score, right? And then normal CDF is where we have a z-score and we want to find the percentage. So the way you type in invert norm is you type in pretty much just whatever the percentile it is. 0.95 for 95%, 0.85, 0.75, and so on and so forth. For normal CDF, what you do, this is a little bit different. For normal CDF is you need a top bound and a bottom bound, right? So normal CDF. So the top bound is gonna be, or sorry, you start with the bottom bound. So if you wanted to find, like, let's say you wanted to find everything from here this way. So the bottom bound, you would type in something like really small and negative. So negative like 100, 1,000 something. And the top bound, let's say this is, we'll use this as a z-score. So this is 0, this is 1, so this is like -2. And then you would type in your mean, which is 0, and your standard deviation, which is 1, okay? If they gave you these and these weren't z-scores, that would be fine. You would just change your mean, your standard deviation. Same thing for invert norm, okay? All right, central limit theorem. So here's what is going on with the central limit theorem. Let's say, I'll do my work over here. Let's say you have a population, right? And it can be whatever you want it to be. So let's say I have a population of just people. Let's say I'm looking at heights. So if I'm looking at heights, this can be whatever shape it needs to be. So the population can be skewed right, it can be skewed left, or it can be relatively normal. It doesn't really matter. What the central limit theorem says is when you take out a sample and you find its mean, so if I take a sample, so let's take this little sample out here, and I find its mean, and I find another sample and I find its mean, and I find another sample and I find its mean, and I find another sample and I find its mean, and I find another sample and I find its mean. All those means are going to be normally distributed, meaning it doesn't matter what the shape of my original population is. When I take a sample of the means, the means will be normally distributed. The population mean will be the same as the sample mean. And the standard deviation will be the same, but we don't call it the standard deviation, we call it the standard error, and we divide by the square root of how many we took in the sample. Okay, so here's how you can think about it. If I have a sample of people, the sample can be skewed. It can be skewed right or skewed left. But if I find the mean, what that's going to do, after I find the mean, is it's going to, the means aren't going to be that spread out, right? You find a sample, the sample might be spread out, but when you take the mean of that sample, so you divide by 5 or divide by 10 or divide by 12 or whatever it is, what that's going to do is it's going to take the sample and it's going to take the original population, it's going to shrink down the standard deviation. So the more things you have in your sample, the more the standard deviation is going to shrink down. Let's do a couple examples. So the mean and the standard deviation. So these are the population mean and the population standard deviation. Find the mean and standard deviation. We don't call it standard deviation in a sample, we call it standard error for a sample distribution of size 4. So if I wanted to find this, the mean is going to be the same as my mean in my population. So the mean is going to be 90. Now this curve represents all the different means of size 4 that I can get. So normally the standard deviation would be 4, but since it's a sampling distribution, you have to take that and you have to divide by the square root of this, which is 4. So 4 divided by the square root of 4 is 4 divided by 2, which is 2. So the standard error, the standard deviation of my sample means is going to be 2. So it's going to be shrunk down. Same thing here. So we do the same thing here. This is going to be 90. All these are going to, the centers will be 90. The centers will not change, right? And the standard deviation is going to be the old standard deviation, but then we have to divide by the square root of n, which is 10, because that sample mean is going to shrink the standard deviation up. The bigger the size, the smaller my standard deviation is going to be. So let's find that real quick. So we do 4 divided by the square root of 10, and that gives me 1.26. So you can tell if I went from a size 4 to a size 10, my standard deviation is shrinking from 2 to 1.26, right? Same thing here, size 20. So let's go ahead, draw our curve here. 90 will go in the middle, and then size 20. So this will be my original standard deviation divided by the square root of 20. So 4 divided by the square root of 20 gives me 0.89. So you can tell that the standard error, the standard deviation of my sample distributions is shrinking down. It's going to get smaller and smaller and smaller. As n gets bigger, as the number that I take out of the sample increases, this number will get smaller and smaller and smaller. So the means will be less randomly distributed, or less spread out as n gets bigger. Hopefully that makes sense. All right, let's do a quick example real quick. Basically, these are going to be the same as what we've been doing, but you're going to have a new standard deviation. Real quick, as a side note, you can only do this theorem if two things happen. One, the original has to be, if the original, so we'll call it the OG, if the original is normal, then it doesn't, N-O-R-M-A-L, close enough. If the original is normal, then you can go ahead and you can go about the theorem. Or if n is bigger than, and for some people, we can just say n is big, but if n is bigger than 30, then we're in good shape. If n is smaller than 30, then it's not going to work. Okay, let's do this real quick. Bank auditor claims that a credit card balance, so someone's credit card balance, are normally distributed with a mean of 2,870 and a standard deviation of 900. What's the probability that a randomly selected credit card balance has a mean less than, or has a balance less than 2,500? So this one, we're not dealing with means, right? So we're actually not going to use the central limit theorem because we don't have a mean to deal with. So goes in the middle, 2870, and then the standard deviation here is going to be 900, and then this number right here is going to be 2,500. We want to figure out the probability, 2,500. We're going to figure out the probability that we're less than 2,500. So you can do this a couple different ways. If I were doing this with the calculator, you could find the z-score and then kind of work backwards. But I would probably just do normal CDF because we're looking for a percentage. The low bound, so we want something really small, so like negative 10,000. The high bound, 2,500. And then the mean, 2870. And the standard deviation, 900. Right, and that will go ahead and that will give me the probability. Okay, so if I type that in real quick, second distribution, negative 10,000, or you can have whatever it wants to be, something negative big. 2,500. Normally it's 0, but we're going to change this to 2,870, and we're going to change this to 900. Normally it's 0 and 1 for z-scores, but we're going to bypass the z-score step here, so I get 0.34. So 34% of the time that should happen, 3405. Okay, now compare that to this one right here. A randomly selected, so you randomly select 25 credit cards at random. What's the probability that the mean, those little things right there, that you have a sample size, and you're looking for the distribution of means, you're looking for the mean balance to be under 2,500. So this should be a lot smaller, because if you have one person under 2,500, that's acceptable. But to have an average of 25 people be less than 2,500, that's really, really tough. So let's go ahead, set this up real quick. This will be 2,870. This will be slightly different. We'll come back to that in a second. And then this will be 2,500. So we're looking at sample means this time. So to find the standard error, what I have to do is I have to take 900 and divide by the square root of 25. So my new standard deviation is 900 divided by the square root of 25, which is 180. So that's my new standard deviation. So now if I want to answer the same question, I'm going to do normal CDF, type in something negative and big, negative, it could be negative 10, negative 30, negative whatever, negative 45,000, top bound 2,500, mean, which is not going to change, 2,870, and standard deviation, which we just found a new standard deviation for the sample means, which is 180. Let's go ahead and type that in real quick here, change that to 180, see what I get. 0.0199. So you can tell that's 2%, much, much smaller. Right, so big picture stuff, central limit theorem. If you have a sample mean, so if you're building a sample, or you're building a curve out of all these different samples from a population, and you want to find the mean, it'll be the same as the population. If you want to find the standard deviation, you do the old standard deviation of the population divided by the square root of the size of the sample. Okay, let me know if you have any questions.